Hello and welcome to the Algorand Proof of Stake Show, a show by algo devs for algo devs. Here we explore the current state of the Algorand ecosystem by focusing in on interesting projects building out the decentralized future. I'm your host, Ryan Fox, developer advocate here at Algorand. Today my guests are both colleagues of mine, Noah Grossman, project manager, and Idan Meshita, engineering team lead. Welcome to the both of you.
Hey Ryan, how's it going?
Hey,
So good. Well, I know it's good morning to you there in Boston at the new office launch. I'm here in Korea, so it's evening time for me. So wonderful to have you both here.
Yeah, it's great to be here. We've kind of been in office together, which is nice because we don't work in the same place. I live in New York, Idan's elsewhere, and the whole kind of crew's been together in Boston this week, and we didn't really plan it, but our consensus upgrade just went into effect yesterday while we were all in office right before our all hands. So we're all like in the back of the room, like huddled around our computers, trying to verify that the first state proof went on chain, and we saw it, and it was really exciting. So it's been pretty fun.
Yeah, I was definitely having some FOMO going on as I participated in the all hands meeting remotely. Evening time for me and morning for you when the activation happened, and it was really exciting because I know Paul was there and he's like, look at the block explorer. Look, the fact that our block times have reduced. Like we're down to 3.7 seconds now for block latency, block finality. In fact, So I gave a talk today. I'm at the UDC conference here for Upbit in Korea, and I had to go in and edit my slide just before so that I could reduce that number from 4.5 seconds down to 3.7. So it was really thrilling to have that happen. I know the other thing that we really want that came in that same release yesterday is really the kind of the topic of the day today. We're going to be talking about state proofs that now that they have been activated, and then also hopefully you guys can touch a little bit about the upgrades to AVM 7 and maybe building out oracles and randomness beacons as well. So I think we've got lots to cover here today. I want to again welcome you both, and then maybe Don, I'll start with you. Tell us a little bit about what your role is, where you're located. We know you're in Boston today, but where in the world are you normally working, and what do you get to do for us?
so Algorand has an engineering team in Israel, in Tel Aviv, and I'm the team lead there, and we have 4 people in the team, and we are focusing on state proof. That's what we have been doing for the last year, something like this, and yesterday was, in some sense, the finish line for us in this project. So this was live on mainnet, and it's great.
Well, good. And Noah, how about yourself? I know you work in New York, so not too far away for you to come and join in the Boston office. But what is it that you get to do on a daily basis?
Yeah, so I'm a product manager, so I basically try to figure out like what's important to work on and why. So Idan and I work very closely together. We partner on figuring out like all the right decisions to make state proofs as great as they can be. We've got some fun stuff coming. Like the story isn't over quite yet. We've got more stuff coming in the next couple of months as well. But yeah, I really just partner together with Idan to figure out what we should put on the roadmap, try to make sure it all gets done in the right timelines. I face externally sometimes. I do market research, and I also work on our performance team. So I'm also working with the guys that are trying to make our blockchain a little bit faster and more scalable. So that's where I've been at so far. And yeah, it's a really fun job.
Absolutely. Well, good. Well, we're glad to have you both here on the Algorand Proof of State show. And I think with that, I'm gonna turn it over to you guys. Why don't you tell us a little bit about what the finish line looks like, kind of what's now possible, and how you use it. So I'm gonna step back and let you guys go for a while.
Yeah, so I guess we could first start with like the problem here. So blockchains are great, right? Each blockchain is kind of like its own crypto nation that has its own set of currencies and users and artists and developers that all can create and exchange value in a decentralized fashion. But the problem is that these different ecosystems don't talk to each other. There's no way for blockchains to natively communicate with each other. So instead, there's been these trusted middlemen that have kind of come into the picture that try to connect these blockchains together. And people might be wondering, well, why would you go cross-chain? Algorand's great. Why do I want to care about other ecosystems at all? Well, while Algorand has a great and thriving and growing ecosystem, there's a lot of other exciting projects out there. And we don't want to limit the Algo fam to only projects that have been built on Algorand. People are going to try to go cross-chain, and we want to provide secure interoperability rails that let them get there and come back more safely. So there might be new projects over there, or let's say I have an Algorand account that's, let's say there's some crypto bank that's built on Algorand, and there's another one that's built on Ethereum. And I've got an Algorand address and you've got an Ethereum address. There'd be no safe way for us to even just do basic transactions among ourselves without having some secure interoperability infrastructure. There's also other benefits like having access to more liquidity across multiple blockchains. So there's a lot of reasons to go cross-chain, and we want to make it safer and easier to do so. So I guess if you think of like a bridge, how it typically works, you lock some tokens on one side. Let's say we're trying to go from Algorand to, say, Ethereum. You'd lock the algos on one side, and then you'd try to mint a wrapped version of them on the other side. So you're kind of creating like this IOU that says, I have some actual value, some algo tokens locked somewhere else, and I'm creating an IOU wrapped version of it. But in order to convince people to actually utilize this wrapped version of the token, you need to have confidence that there's actually something there on the other side. And currently, there's usually some set of intermediaries or middlemen that try to provide those assurances. But even if these middlemen are honest, we know that they can and have been hacked. So in order to be able to use this wrapped version, you want to have confidence that there's something you can redeem on the other side. So you're kind of creating this single point of failure.
So in some sense, you have a machine, right, on the other side that mints stuff, right? So you were saying that it is backed up by something real, but someone needs to convince the network, this machine, this smart contract, that this thing actually was locked and it's not usable. Because if not, then you're just minting, you're just printing money, right? You're just printing values, right?
Exactly. We're not a treasury department. We're not in the business of just printing money out of thin air. So in order to print money, you've got to lock it up somewhere else.
Yeah, and you need some guarantee that it is locked.
Exactly. And right now, those assurances try to come from these these middlemen that are trying to do a great job, but it's easy to create some set of validators that try to prove activity, but it's really hard to do that in a decentralized, trustless manner.
So the middleman actually has a way to communicate with his smart contract on the other network, and basically they are talking to each other and they are convincing that, yes, I've seen that. They basically create some proof, signature or something like this, that convince the other party that this actually happens. And there is a trust system between those middlemen that have a look, have a vision of what's going on the other chain, and they convince the other side, right?
Yep, exactly. So, we want to reduce like the trust assumptions when you try to go cross-chain.
Yeah.
So if I'm going from Algorand to whatever other blockchain you'd like, ideally you wouldn't have to trust anything but those underlying blockchains themselves and the smart contracts that actually do this locking and minting, these locking and minting actions. And I think that's kind of like a good intro to like where state proofs come in. So we kind of described this validator scenario that it's easy to build a validator, but it's hard to do it in a decentralized, trustless way. State proofs really simplify and secure this really hard part of building a bridge, which is validating cross-chain activity in a trustless, decentralized fashion. So you're the expert here. Do you want to tell us a little bit more about like what state proofs actually are?
Yeah. So the idea is why to trust those middlemen, because we have consensus mechanism, we have participants on Algorand. Why don't give them the ability to do the same thing? Meaning that let's try to export something, some summary of what's going on the network in this period of time, and be cryptographically sure that this is correct. So that's what's going on with state proofs. So state proofs are some small cryptographic proofs, okay, that comes from the Algorand network and export a summary of what's going on in the last 256 rounds, what happened, what transaction were occurred, and that's the idea. So going back to Algorand, so we have participants. So everyone, in some point of time, they summarize what happened in the 256 rounds ago into one hash value, and everyone signed that. Every participant in Algorand signed it and send it or propagate that over the network. And we have those relays that basically connect all the participants together, and they gather all the signatures, and then they produce a proof. And this is the nice thing about the proof. So you can think about that. I could just, for if I want you to convince you, if you are outside of Algorand, so I will just show you all the signatures. Look, he says this, and he says, and everyone says the same thing. So this might be the case, right? This is the truth. But the nice thing here that you could create a proof which is much smaller than just give you everything, right? And this go to a trick called interactive proofs, in which you have some knowledge, right? You have some knowledge. You know, like for example, you have a bunch of signatures, or you know the difference between a Coke and a Pepsi, right? You have the ability to know that, and we could play a game of guess, meaning that the verifier challenge the prover and say, okay, so you're saying that everyone says the same. Okay, so please present me the signature in this position, and I will send you this signature, and you verify the signature. So, yeah, this person says that this is correct, and then you challenge me again. And the nice thing here is it's it's secure with with very high probability. Like you don't see everything, but as you go over this game and you play this again and again and again, you gain high confidence that I have this knowledge.
Okay, so basically, so first, rather than having some third party summarize what's happening on Algorand and saying that to other blockchains and other, outside the Algorand network, the very network participants that advance consensus and verify transactions will summarize the transactions they've seen over some period of time. In this case, it's 256 rounds, and everyone creates this summary data. And then these same network participants will sign it. So they publish these signatures that say, I vote that this is a summary of recent Algorand data. And they send it to these relays that connect all the participants together.
Mm-hmm.
And then, as you're saying, like the naive approach here is to just have some validator, which is basically the application or the smart contract on some other blockchain or some other area, rather than have them validate every single signature, which could be, pretty beefy over time, especially as the network becomes more decentralized.
Mm-hmm.
State proofs include these really nice cryptographic tricks where you basically have the validator challenge the prover or the relay that created the state proof to selectively reveal specific signatures.
Yeah, and the probability goes as the probability grows, and you could be confident that what you've seen is correct.
Got it. Because if you check one signature, then you're like, okay, I have one person's signature, and
Yeah.
they might be lying, they might not be. But as I challenge more and more signatures that I select as
Yeah.
the validator, I have more confidence that the state proof is valid, because it's pretty hard to like forge like these
Yeah,
signatures
and
over time as you gather more of them.
yeah, in some sense, you are convinced that I've seen everything. That's what I'm trying to convince you, that I have all the signatures from everyone, and I'm just presenting you a challenges.
Got it. Very cool.
Yeah, and so the relay, so he gathered all the signatures, and then he creates a proof, and he writes it on chain. And this transaction, it wraps it in a transaction, in a very specific transaction, and this goes into consensus, like all normal transaction in Algorand, and all the committee members, it's their turn. They are verifying the proof to make sure that this relay was not lying and it didn't like made it out of thin air. And once they agree, it's written on chain.
Got it. So we don't have to trust the relay that aggregated these signatures because one, they didn't produce them, and two, they just not compressed, but they do this game of constructing this cryptographic proof that can then be verified. And what you're saying is the same Algorand participants that advance consensus will also validate this proof that was generated.
Yes.
So similar to how other transactions go through consensus, state proofs are also validated through consensus.
Right. So you will not find a false proof written on chain. So no malicious user could inject some proof which is not correct.
Got it. So if I see a state proof on chain, I have confidence that the Algorand network A produced it and B validated the proof that was proposed.
Yeah.
Cool. I mean, that provides a lot of confidence to me.
Yeah.
Okay, so we talk about state proofs as being like a chain. What does that mean? How are these state proofs actually like chained together over time?
So if we go back to what signatures are, right? You need a public key.
Mhm.
So I've said that everyone like they gather signatures and they reveal particular signature within what they have. But how could the verifier make sure that this is correct? That like this is a signature for someone who they trust? Because like a bunch of people could just create a state proof, right? So you need something. You need some commitment, some summary of the people who are going to create a state proof.
Got it. So you're saying that like, some random group of people could try to create a state proof and they could create a state proof, but it wouldn't be legitimate from the Algorand blockchain perspective because the signatures, as you're mentioning, have a public and a private key.
Yeah.
And we have to make sure that the signatures are coming from actual Algorand participants. And you're saying that there's a commitment on chain to who the participants are that will sign the next state proof.
Yeah.
So when the state proof is actually validated, you actually check to make sure that these signatures that compose the proof are coming from the Algorand participants that were committed to in advance.
Right. So a third party, in some sense, when he verified the proofs, he needs some public, like summary of the public keys for the people who generate the state proof. So in some sense, if I'm a third party, then I need those things. So the idea is to chain that, meaning that if I'm verifying a state proof, I'm getting like a summary of what's going on Algorand network, but also I will get a commitment or a summary of who would be the next participants that would generate the next state proof. So I'm anticipating this. So if I'm verifying a state proof and I'm being convinced that this is correct, like this is the Algorand network in this period of time, I'm also being given a value which I could use to verify the next state proof because I know who is going to be part of the next state proof. So this is why it is a chain.
Got it. So, and like any chain, there has to be some initialization data that says, here's the first participants that will sign the state proof. But once the first state proof then gets written on chain after that, it also includes information about who is going to sign, who being participants on the Algorand network, who is going to sign the next one. And they get chained together. So any validator that wants to, validate Algorand transactions in new environments, this validator has to validate signatures coming from the participants, which are chained together through state proofs.
Yeah, so it will start with some Genesis participants. That, by the way, this is also being agreed upon on consensus. So everything is extracted from on-chain. Everything is agreed with consensus.
Got it. Okay, so we have this chain that that contains summary data about Algorand state, as well as the participants who are going to sign the next one. But what's this whole post-quantum thing? Why do we consider state proofs post-quantum secure? And like, what does that actually provide assurances of?
So the cryptographic construction of state proof relies on two primitives, which are post-quantum secure. We introduced the Falcon signature scheme, and we use that for participants. They're using this scheme in order to sign the state proof, and all the hashing within the state proof is being used with a post-quantum secure hash function. which we call some subset sum hash function.
Got it. So the underlying cryptography that composes state proofs is post-quantum secure, which means a quantum computer, a powerful quantum computer, could not forge a state proof or even insert fraudulent transactions in the history of the blockchain because it would have been caught by state proofs.
Yeah, exactly.
Got it. Very cool. So I guess we have these nice fancy state proofs. Let's talk a little bit like how we can actually use them. So we've kind of alluded to the fact that they can be verified because they're portable proofs outside the Algorand blockchain. We've talked about these like state proof smart contracts. How do I actually take advantage of them as a developer in the Algorand ecosystem? What kind of applications can I build with them, and how am I going to actually interface with state proofs? Am I going to interface with them directly?
Yeah. So as we said, like you could export state of Algorand outside of Algorand, right? And in some sense, you could create some kind of an oracle, right? You could create a program that is given state proof and run the state proof verification algorithm. And if it's convinced, it has a summary of what's going on in the past 256 rounds, right? And then you can program this thing on chain, for example, Ethereum, other blockchain, and you will have an oracle which basically you could ask questions, right? This is the replacement of the middleman in some sense. Like we go back to the problem that we had, right?
Right.
So now you have an on-chain oracle that you could ask question, and you ask, this transaction actually occurred in Algorand? And it would say yes. That's the idea.
Okay, so basically we can build these programs or these smart contracts on other blockchains that verify state proofs and kind of become like an Algorand oracle. And when I say oracle, it's something that learns and cryptographically verifies Algorand state, and then because it learns that knowledge, these summaries, and they can store them over time, they can then answer questions about if specific transactions occurred in specific Algorand rounds. So I think the really interesting use case there is once you have these light clients or these state proof smart contracts written on other blockchains, applications in those ecosystems can then cryptographically secure, in a cryptographically secure way, validate Algorand transactions. So going back to the bridge example, if I'm trying to mint some wrapped algos or some other ASA on Ethereum or some other blockchain, rather than turning to some middleman and asking, hey, did Idan actually lock up 10 algos in this round when he was trying to bridge it over to Ethereum, you can ask this state proof smart contract, is this Algorand locking transaction legitimate? And
Actually occurred.
Did it actually occur? And you get that confidence or those assurances directly from the Algorand network. So you're kind of bringing like a window from Algorand itself onto other blockchains that allows you to much more safely mint these tokens without knowing that there's some value that's backed on Algorand for these IOUs.
Yeah, exactly.
Great. So I guess what's coming next? What can we expect next from state proofs now that they're live?
I guess now state proofs are designed to be 256 for every 256 rounds. And first, we want to do a little bit faster proofs to generate the proofs more faster, to reduce the time it takes to learn. The oracle will learn what happened. So this is the first thing, and this is what we will focus on. And state proof could be used for cool stuff on Algorand. For example, we could use that to make sure that our catch-up is post-quantum secure. We could use that to fast catch-up, right? We could validate the proofs all the way to the end and make sure, like this is the current round, everything is correct. And we could jump in some sense, like state proof gives you the ability to jump, to leap forward in the future to 156 rounds instead of in just every block.
So if I'm a new node that's joining the Algorand network, rather than having to validate every single block that's occurred, I can use state proofs as a reference point to summarize the transactions that have occurred and other stateful information. And I can just skip forward in time in a post-quantum secure manner. So I know that, I can basically fast forward the blockchain to, a very recent block and say, I know that this is legitimate. It's awesome.
Yeah.
Cool. Well, yeah, that's state proofs, guys. I don't know, Ryan, if you had any more questions about that, or if there's anything else we could cover that would be interesting.
Yeah, really insightful information about state proofs, and we're really thrilled that those are now available on mainnet as of just a handful of hours ago. I guess maybe where do we get more information as a developer about how to actually generate, or I should say, interact with these state proofs? How can I use these within my Algorand smart contract? And as a follow-up would be, what are the Algorand team building on other blockchains in order to have the state proof prover available for to build these bridges?
Yeah, so first, if you want to learn more about state proofs, we've got a couple of technical deep dives on the Algorand developer portal. There's a new section on developer.algorand.com or .org, I forget which one,
.org.
that talks about .org, that has a technical overview of state proofs and also how to build an Algorand-like client using state proofs. Now, one thing to note, we didn't talk about this quite yet, but we've kind of mentioned beforehand that we're also working on creating ZK snark proofs of state proofs. So a snark proof is basically, it's a proof that someone else has seen and verified a state proof, but in a much more compact manner. So in a handful of bytes, you can basically verify state proofs in fee-constrained environments like Ethereum. So our crypto team that we partner with is hard at work on that, and that should be coming out soon. So for some blockchains or for some groups that want to build light clients, but want to use the most compact proof possible, snark proofs will deliver that compactness. And then I think your other question was, how do I actually interact with them on other chains? So we're working with some groups to build an Algorand light client and other blockchain light clients on Algorand. So you have a pair of trustless light clients that connect to two ecosystems. So we can build an Ethereum light client on Algorand that allows Algorand developers to verify in a trustless manner Ethereum transactions. And then we can build an Algorand light client on Ethereum that lets Ethereum applications trustlessly verify Algorand transactions. So bridges are more useful if they're two-way. Like you don't want to just go from Algorand to Ethereum. You want to also be able to go from Ethereum to Algorand. So with this trustless light client pair, you can effectively validate both blockchains in each other's context, which allows you to move from one direction to the other and back.
Great. We're really excited to see those come down the line. I guess as a last question, just how do we connect with each of you? Like, where is the best place to connect with you to provide feedback about the features that we need for state proofs, and where do we get more information from you guys? Are you guys on social media? Where do we connect with you?
Yeah, so if there's any kind of feedback or you want to engage directly with the community, Discord's a great place to talk. There's a pretty active community there. You can also find us at least I'm on Twitter, at Noah Grossman TM, because at Noah Grossman was taken. Are you on Twitter as well?
Yeah.
Yeah?
Yeah, we can advertise the name afterwards. I don't recall that.
Got it. Yeah, so we're on Discord and Twitter.
Outstanding. Well, Idan and Noah, I want to thank you both for joining me today on the Algorand Proof of Stake show to talk about state proofs and the performance enhancements that we recently added into the Algorand mainnet. And with that, I will say thanks once again for joining us.
Thanks for having us.
Until next time, have fun building on Algorand.